You all know me as the integrals guy. I solve integrals for a living on YouTube. And over the course of the past year and about 250 videos, I've solved lots and lots of integrals, which feels awesome. But for some reason, I'm yet to solve many famous integrals, and the Bernoulli integral is one of them. And since we're in the holiday season, I might as well present you with the solution development for the nicest Bernoulli integral. I call this one the nicest because it evaluates to a result that is almost too good to be true. It is incredible. And the solution development is pretty cool as well. So let's get started. How do we approach this thing? Well, our integrand is x to the negative x, so we might as well write this in the form of an exponential function by recalling that we can write x to the negative x as e to the negative x times log x. And the reason I want to introduce exponential functions is because these things have really cool infinite series expansions. Recall that e to the x can be expanded as the sum over the non-negative integers k of x to the k divided by k factorial. This means that e to the negative x times log x, that's our x to the negative x term, this can be expanded as the sum over k. We have this negative 1 here, so that's negative 1 to the k times x to the k times log to the k of x divided by k factorial, meaning that we can write our target integral I as the integral from 0 to 1 of the sum over k of negative 1 to the k times x to the k times log to the k of x divided by k factorial integration with respect to x. And now it's time for the age-old question of whether or not we can switch up the integration and summation operators. Well, that depends on boundedness and convergence. If there are no problems regarding that, then yeah, sure. So let's do some quick checks first. Notice that we have an infinite series over the k variable, and we have this alternating term in the numerator and this k factorial term in the denominator. So no problems there. Now what about the behavior of the functions of x as x approaches 0 and x approaches 1? Well, for the limit as x approaches 1 of x times log x, we get 1 times 0, which is 0. So the limit is defined here, and it's also defined for all the integer values of k here. Now what about the limit as x approaches 0 of x times log x? We'll write this as the limit as x approaches 0 of log x divided by 1 by x, meaning that we have an infinity by infinity form for which we apply L'Hopital's rule and differentiate upstairs and downstairs. We have 1 by x divided by negative 1 by x squared. We expand by x squared. Terribly sorry about that. And we have negative limit as x approaches 0 of x, which is 0. So again, the limit here is defined, and it'll be defined for all the integer values of k here. Okay, so no problems regarding boundedness and convergence. So yeah, we can switch up the operators. We now write I as the sum over k of the integrals from 0 to 1 of negative 1 to the k divided by k factorial times x to the k times log to the k of x dx. And the negative 1 to the k by k factorial part is independent of the x variable with respect to which we're integrating. So we take it outside the integration operator. And finally, we have I equal to the sum over k of negative 1 to the k by k factorial times the integral from 0 to 1 of x to the k times log to the k of x dx. The integral we now have is pretty easy to evaluate. We'll call this I sub k. So I sub k is the integral from 0 to 1 of x to the k times log to the k of x dx. We'll make a substitution by letting negative log x equal to u, which implies that x equals e to the negative u. And this also means that dx equals e to the negative u du with an extra negative sign. And as far as the limits are concerned, as x approaches 0, the logarithm will approach negative infinity. So the lower limit is now positive infinity. And as x approaches 1, we have log 1, which is 0. So that's the integral from infinity to 0 of x to the k, which is now e to the negative k times u. And log to the k of x would be negative 1 to the k times u to the k, and the differential element is now negative e to the negative u du. So we switch up the limits of integration to get rid of the extra negative sign, and we have the integral from 0 to infinity. And this negative 1 to the k thingy is independent of the x variable, and we're left with u to the k times e to the negative k plus 1 times u on multiplying the two exponential functions. And this integral looks a lot like the gamma function, so let's turn it into one. We're gonna let k plus 1 times u equal t, which implies that du is now dt by k plus 1, which implies that I sub k is negative 1 to the k times the integral from 0 to infinity of u to the k is now t to the k divided by k plus 1 to the k, and we have e to the negative t dt by k plus 1. Again, we have these k terms independent of the x variable, so we take them outside the integration operator. We have negative 1 to the k divided by k plus 1 to the k plus 1 times the integral from 0 to infinity of t to the k times e to the negative t dt, which we recognize as the gamma function evaluated at k plus 1, which is k factorial. We now return to the target integral. So we have I equal to the sum over k, terribly sorry about that, of negative 1 to the k divided by k factorial times the result of I sub k, which we have as negative 1 to the k divided by k plus 1 to the k plus 1 times k factorial. So we have some cancellation taking place. Negative 1 to the k squared is going to be positive 1. So we have I equal to the sum over k starting at 0 of 1 by k plus 1 to the k plus 1. And if we transform from the k plus 1 to the k realm, this means that our target integral, that is the integral from 0 to 1 of x to the negative x dx, equals the sum over the positive integers k of k to the negative k. So the continuous sum, that is the integral, equals the discrete sum, which is awesome. I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.